All right, everyone. Hello and welcome to our next primer video. So this one is going to be on systems programming. Now I know the class is going to be on systems programming, but I wanted to give you a rundown of some of the basic systems elements that we're going to be interacting with. The intro video should have a more conceptual look at like what systems is and what systems programming is. But for this, we're going to go over some very specific elements of programming systems, particularly in a Unix environment, so on a Unix operating system. One thing to review once you're actually at that point in the class is the Unix operating system section of the slides. Usually that's going to be page 135, roundabout there. I've actually copied over the notes from the notes section of the repo to right over here. So, because I did want to go over this first before we actually look at the code here. So first of all, let's quick review. What does an operating system do? Well, the core of the operating system is it can multiprocess, it can support multiple users, and usually it can support a file system. Now, the multi-process and multi-users are probably one of the most important parts, the most core parts, because that like the first operating systems were these were systems that were used to replace batch processing. So what it used to be is you'd have a big university machine and you'd submit your code to be put on a job for that. And that wouldn't even necessarily be, in the earliest days, that wouldn't even be like a software queue. That's like an actual queue of, you line up the cards that you're going to put in, you know? But eventually, their system was created to replace batch processing, where we can actually have multiple programs from different users running at the same time. And it grew from there to include stuff like dealing with the file system, including things like networking drivers, device drivers. Eventually, of course, we got graphical interfaces that would come packaged with the operating system. And, you know, it's funny because things like Linux, Linux distros will be packaged with a graphical interface, but they don't have to, and they're not actually under the umbrella of Linux usually. Usually it's a separate piece of software, and you can swap out. You can say, all right, I want to run this graphical environment instead of this one. So it's kind of interesting on whether that is or isn't part of the OS. For sure, on things like Windows, it is. This will also sometimes grow to include things like the standard programs, certain text editors and stuff that are built into the operating system itself. This can include common libraries that are used and basic security utilities. So the operating system can be quite big. Usually, though, when we talk about the OS in a computer science context, we're talking about the kernel. So this is going to be something that is ring zero, something that is in kernel space, they call it. This is a part of the system that has certain privileges over user space. And that's usually the dividing line between kernel space and user space. And importantly, this kernel space and user space can communicate with each other, but not very openly. Usually we're not going to have things where we have any sort of direct access. We're not having direct channels for user space programs to edit kernel space information, because of course we don't. That'd be extremely dangerous. But what we can do is use system calls. So system calls are going from user program to operating system, user space to kernel space. These are special functions. These are functions just like you'd see like this in the same way that we have strlen as a function. You're going to be passing it arguments and all of that. But they're special because they actually make that transition during the call from user space to kernel space. And there's also a lot of functions that are wrapped around these. So for example, printf is not a system call, but printf uses a system call. It's using the right system call. But it itself is not a system call. This does include things like read, write, open, close, exit, kill, exec, fork, changedir, chmod, chown, and you can actually get a good look at a lot of these at Man 7. But yeah, these are kind of the atomic functional unit of systems programming, is using these systems calls. Signals work the other way. So signals are going from operating system to user space. These are usually in the form of interrupts that are letting the OS handle things in the user program space by interrupting it, and there'll be some handler attached such that we can, given an interrupt, take certain actions. You've definitely seen a few of these before. SIGINT is what happens when you type Control-C. It sends an interrupt signal to the program. There's also SIG-SEGV. You've definitely seen that before. If you haven't, then wow, I'm impressed. That's segmentation fault. That's what happens when there's some sort of memory error going on. You're writing outside of what you should be writing in. And the OS will say, oh, no, can't be doing that. Send you a SIG-SEGV. SIG-pipe is also one you'll probably see in this class at some point. This is what happens when you try to do I/O with a broken socket or a pipe. Usually it's when you try writing to a pipe that's already been closed on the other end. And this could be an actual pipe, like in shell programming. If you don't know about that, don't worry. We cover that a lot in class. Or this could be a socket, something going to TCP socket or something like that. And again, you can look at all these signals, Man 7. Now, processes. These are the basic unit of execution for the computer. It's managed by the OS. All of them are going to have their own PID. They can contain multiple threads. So we don't actually have one process isn't necessarily running one thread of execution. By default, it is. By default, there is going to be a process and a thread, one thread in the process. But that doesn't need to be the case. Of course, you can create new threads, and they will be created within whatever process you're running. There's also usually, and by usually I mean pretty much all the time, this is only on very weird operating systems when this isn't the case, there's going to be an exclusive pool of memory. So there won't be any sort of real way without doing some interesting things to access the memory between processes. If you're running one process 1, running process 2, and process 1 looks at a variable, it's going to be, it can be in the same virtual memory space as another one, but they're going to be different values. They're going to actually be mapped to different parts of memory. So it's exclusive memory. It's going to have its own little stack and heap and text and BSS and all that. It's also associated with an entry in the process table. So the process table is being maintained by the operating system. It's going to be indexed by the PID. And that has all sorts of information that we'll talk about in the next little section there. It also, if you want to create a new process, the most straightforward way and the way we use in this class is with fork. So fork is a system call. That's going to, you got one process, that's going to split it into two processes, a parent and a child. And the child is going to have an actual copy of the parent's memory space. So if the parent has a variable a equals 5, and the child would also have a variable a equals 5. However, if the parent then changes a to 7, a equals 7, the child doesn't. The child still has a equals 5 because it's a separate memory space. But yeah, fork is important. It lets us split off a new process. So the process table. This is going to, of course, by indexing, include the PID. It's also going to include the user ID, which user has the process at the moment. It's going to have a current directory. So every process has its own current directory. If you're CDing, if you're using CD on the terminal, that means that the terminal's process has that directory. But every program has its own current directory as well. And that information is stored in the process table. This will also contain arguments that have been passed to the program. This will include, the first argument, of course, will be the name of the program, just like it is in normal C arguments. It will include the environment of the process, so all of the environmental variables. We'll learn more about those in the future, but note that. Also a list of open file descriptors. File descriptors are very interesting. We'll talk about them in a second, but they, at default, at the start, it's usually going to be 0, 1, and 2, specifically standard input, this guy, standard output, 1, and standard error, 2. There'll also be some other OS information about things like memory, program info, like the program counter, but that's nothing we have to worry about during this class. File descriptors. So we just talked about those a little here. File descriptors are, we can think of them almost like a pointer, but instead of pointing to a space in memory, it's pointing to an open object in the file system. Now I said object intentionally here because it's not necessarily a file. It could be a file, text file, image file, whatever. It could also be a device. Because you see in Linux, everything's a file. A device is a file. Any interface is a file. This is any part of the system besides memory itself, basically, or the registers, is going to be associated with a file. And if you open that in a program, in a process, it is going to open that with a file descriptor that's pointing to it. And the nice thing about this system where everything's a file is that the same system calls work for anything. So if you were to call write on a file descriptor, you call the write function to write some bytes to a file, hopefully that would be handled in much the same way as writing to a device, because you're just writing to a file descriptor. File descriptors are also kind of the language in which we speak to system calls to, as far as doing any sort of I/O. So writing, reading, opening, these are all done with file descriptors instead of things. Well, open uses a file name as well, but returns a file descriptor. So we would never write, we'd never use the write function with a file name. We'd open the file and have a file descriptor and then write to the file descriptor. So these are very important. And the last thing I wanted to talk about before we get into the code is threads. So threads are, you can think of them like lightweight processes. That's, if you ever see LWP, you'll see that in this class. You'll see different counters and stuff will have a term LWP that stands for lightweight processes. That's threads. These don't have entries into a process table and no exclusive memory and no PID. So if you have two threads within one process, and one changes a variable A from 5 to 6, then that variable is also changed for the other thread. Threads are sharing memory because they're in the same process. They're just another thread of execution. Now the PID, this is not 100% true. So threads, a lot of the time threads are implemented mostly or fully in user space, while processes are always implemented in kernel space. So they have very different systems they're working with. The PID is something that is associated with that process table. Meanwhile, the threads, they will actually usually have an ID as well, but they don't need to because that's going to be just the handler for some library or something like that, not the operating system itself. So yeah, they might have an ID, but it won't be a PID. It's not going to have a process table entry. It's not going to have memory besides that it's sharing with the rest of the process. And also, if you're using this in this class, you're going to want to make sure you put the LP thread flag in your compiler, like so, and in fact, like so. So this is our makefile for this one. We have the LP thread. So let's start with main. We have 4 tasks, and we're going to see an example from each of these different functionalities that we're looking at for right now. So first, let's look at our file example. Here we are. Yeah, file example. So we have a string to write, s. We're going to get the size of that string. Size t here. Again, this size t isn't anything special. It's just, I'm pretty sure, an unsigned integer. It's just been typedeft, and that's what C likes to do. C likes to have its weird little types. We're also going to make a buffer here that we're going to use for reading in a little bit, but it's going to be ending up storing the same thing that S does right now. So onward, we go to opening a file. We create an integer fd. This is going to be our file descriptor, or hold our file descriptor anyways. We're going to open foo.txt. We also, again, have this options thing. We talked about this in another video as well, where these are just, this is binary data, these are bytes, and by ORing them together, we can create a list of options. Think of it just like a list of Booleans, but in one byte, because we don't need to waste a whole byte on a Boolean when one bit will do. So we have all these options here that we put together, read or write only. Saying that we want to only allow writing to this file for now. We'll create. If the file's not created, we will create it. And O truncate. So if the file already exists, we will simply write over it. We also give a permissions thing. I use 755 for here. That'll do. If you want to read about Unix permissions, that's its own talk. Then we're going to write to that file. And by the way, all of this like file reading and writing, there's usually a higher level library that you can use that will use, like, you probably see something along the lines of FileStar or something like that. Is that special struct? But that's just abstracting and allowing some more features that this is already doing. This is what's happening under the hood for all of that. So we write to that file. We're going to say what the file descriptor is. Going to give it a pointer to the data that we're writing, in this case a string, and the size of the string is going to be the number of bytes that we write. Also, I did this a little wrong thinking back. I just gave it... That's really dumb. I just put the constant in here instead of the variable name. Good job, Max. Okay, there we go. I feel better about myself a little bit. Let's also make this nice. We'll give it a nice little new line. And we don't even have to update. That's why I had to do string line here, because now we don't even have to update the size. After that, though, we close the file, and hopefully the file will be written to. After that, we can use fd open again. Same file. This time we're going to do read only and ocreate. Don't need otruncate because we're not writing. Don't even really need ocreate, but why not? I start by putting the end of the buffer, putting a null terminator, because always null terminate your strings. That won't be good if you don't. And then we read in that same information to fd, read it in the buffer, size n. Perfect. And that's it. That's how we kind of operate file descriptors. This is the basics of it, and this will be used for several labs doing several things, whether it's writing to an actual file or writing to a pipe. Pipes are used for this, or writing to a socket. There's a lot of file descriptor work in systems programming. Besides that, what was our next one here? I wanted to go in order. Fork. That was up here, I remember. So, how do we create a new process? And how do we separate it from our currently running process? Because the thing is, when it separates, it's not the easiest to figure out which one's the child and which one's the parent. It's pretty easy, but like they're both running the same code. When they split, they both exit fork. In the same code, they're still running the same program. You're not like setting, okay, we're going to set you running on this function like you'll often do with a thread. It's still in the same place in the code in both processes. So in this case, let's create a variable, x equals 100, and we'll call fork. Now fork is going to return a result. If result equals 0, we know we're in the child process. And if result doesn't equal 0, actually, we should also probably have somewhere in here, like else if result is less than 0. If this happens, there's some kind of error going on. And we'll probably just exit with a 1. But yeah, this is an error. But on the other hand, if it's greater than 1, if it's some other number, now we know that this is that number, that result, is the PID of the child process. So at this point, first of all, we'll stick to the child first of all. The child is going to say, all right, I'm resetting x to 50. This is going to change x within the child process and not in the parent process. Then we can say hello from the child process, and my x value is x. Now, in the parent process, we don't want these things to be fumbling over each other as they both try to print. So what we're going to actually do here is we're going to call wait PID result. We're going to pass in this. This is basically a buffer. This is just an integer to store whatever value they send to us. Because this is a return statement, basically, a secondary return. And 0, which is an option thing. In fact, you can see I put the signature there. We don't need any options. And then we're going to print a bunch of stuff from the parent. And this isn't going to return. This is going to wait until the child is done, until the child exits. So we're going to say hello from the parent process. We're going to give the child's PID, what that was before. We're going to see what the return status is. So this return status is hopefully going to be this. It's the same thing that you'll get when you return from main, basically. And lastly, we'll see what the parent's x value is, and it should be still 100 because it changed in the child, but it didn't change in the parent. Separate memory silos. Next, we'll go on to signals. Signals are good. So, how can we take a signal, know it's going to happen, and make it do something else instead? Well, in this case, we're going to set a flag. Basically, what I want to do here is this program's going to enter a trap. It's going to go into a while, what is essentially a while true, a while forever. And we want it to get to this. So the program has escaped and be done. So the way we're going to handle this is we're going to say, all right, we're going to remap Control-C. So instead of killing the program, because normally Control-C interrupts the program, we're done with the program now. Instead of killing the program, what we're going to try to make Control-C do is change this flag variable, which is a static volatile global variable up here. We're going to change that variable to be something different, to be 0, so the while loop stops. But what we're not going to do is close the whole program, so we need to make sure that it continues the program, doesn't interrupt, and goes about doing that. We can do that with the signal function. Also a system call, and we're going to say that sigint, sig_interrupt, should have a new handler, and that handler is going to be int_handler, which is this nice function we made right here. That it requires an integer input, but we don't need to use it. It's just going to change flag for us. And this is how the operating system can then interact with the user space program. And by the way, we're also going to be nice and clean up at the end. We're going to change int_handler back to the default, so we are capable of ending the program still if we want. Save that. And let's take a look at our last one here, which is threads. So in this thread example, we're going to create several threads. The main program is going to just keep creating threads, and whenever it creates a thread, we're actually going to make it stop and use a thread join, and it's going to stop right there and not continue until this thread exits. So we could just do them one at a time. Obviously, that's not the most efficient way to parallelize things, but you could do it, and that's what I'll do here. And it'd be less of a pain in this particular case to do it that way. And the way that this thread helper is going to work is what we want to pay attention to here. We have a local variable, local t, and we have a global variable, global t. So this is going to tell us what thread it is, first of all. It's going to increment all of these except static t. I think I deleted that. Yeah, I deleted that, so that shouldn't even be there. Just get rid of that. That doesn't need to be there. But yeah, we have global t, we have local t. We're going to add to both of them. We're going to print them out, and then the thread's going to exit. So what we should see for all of these is that the local t is going to just be 1 because it's going to add 1 to it, but there'll always be a new local t because it's still within its own little stack space here. It is going to have its own stack space because it is going to be executing its own functions. But it won't be getting its own like memory, the rest of memory, its own heap and things like that. So global t is what's going to hold on to that. Global t is going to have that should keep incrementing with every time. So with all of that said, let's make sure that this is all copied over. Yes to all. I didn't keep it synchronizing when maybe I should. What are you mad about? Okay, it doesn't like me right now. Oh, Unix systems. Okay. All right. Oh yeah, that's. I was like, why is foo.txt there? And it makes that. Anyways, make good stuff. Systems main, and we run it. And hey, look, it stopped us at our Control C. So first we can see that we have our string to write, and yeah, file example worked fine. Fork example, hello from the child process, my x value is 50, very good. And hello from the parent process, the child's PID was that number. Doesn't really matter what it is. Child's return status was 0, very good, that means everything went as it should. And the parent's x value is 100, which is as it should be. It wouldn't have been changed to 50. When we get to our signal, we're currently in our loop, and I'm about to press Control C, and we're done. You see, we were there when we Control C'd, and then the program kept running. We still had the program has escaped. If I were to like magnificently press Control C at like this point instead, then it would have gone out because we replaced the handler with the default. But yeah. And in our thread example, we see exactly what we'd expect to. Local is always 1. Global is actually counting up because as our threads go, we get more threads. By the way, they all seem to have the same ID. That's just because we keep waiting for them to go away. So it's just new thread. Okay, that thread's back in the pool. New thread again, you know. We keep recreating them and destroying them before we create another. So that's it. That's a basic introduction. Obviously, the rest of systems is left to the class itself, which will take a semester and will be very in-depth and hopefully very informative. So with that, I will see you all later. Peace.